let's go. Organic chemistry speedrun, episode 1. All right. Okay, hopefully this works. How's the mic quality? This should be good, hopefully. Alright, let's get started.
Talk about ionic bonds, covalent bonds, particularly polar covalent bonds and non-polar covalent bonds. So let's say if we have this bond, the bond between two hydrogen atoms. Would you describe this bond as ionic, polar covalent, or non-polar covalent? Anytime you have a bond between two atoms of the same element, it's always going to be a non-polar covalent bond. Now, the reason why it's a covalent bond is because the electrons in this bond are shared equally, due to the fact that we have the same the same type of atom. Electrons in this bond are covalent bond. Now, the reason why it's a covalent bond is because the electrons in this bond are shared equally, due to the fact that we have the same the same type of atom, and so therefore they have the same electronegativity, and so they pull on those electrons with an equal force. So because the electrons are shared equally in this molecule, it's going to be a non-polar covalent bond. Now, here's another example for you. What about the carbon-oxygen bond? Would you describe it as ionic or covalent? Now, anytime you have a bond between two nonmetals, typically it's usually a covalent bond. So we need to determine if it's a polar covalent bond or a non-polar covalent bond. And we need to look at the
Yep. We should be good now. We should be good. We should be good now. Hopefully. Hopefully we should be good now. Yes. We should be good now. I think we should be good now.
covalent bond. Now, here's another example for you. What about the carbon-oxygen bond? Would you describe it as ionic or covalent? Now, anytime you have a bond between two nonmetals, typically it's usually a covalent bond. So we need to determine if it's a polar covalent bond or a non-polar covalent bond. And we need to look at the electronegativity values of these two elements. So here are some numbers that you want to be familiar with. Hydrogen has an electronegativity value of 2.1. Boron is about, well, let me list out the elements. Boron, carbon, nitrogen, oxygen, fluorine. So boron's about 2.0, carbon is 2.5, N is 3.0, O is 3.5, F is 4.0. And these values are based on the textbook I'm using. Some textbooks might have slightly different values, but you want to use the values based on the textbook you're using. So carbon has an electronegativity value of 2.5, and oxygen has a value of 3.5. If the electronegativity difference is 0.5 or more, then the bond is said to be polar. If the electronegativity difference is 0.4 or less, then the bond is said to be nonpolar. So 3.5 minus 2.5, that's 1. So therefore, we can say that the carbon-oxygen bond is a polar covalent bond. The electrons are being shared, but not equally. Now, because oxygen is more electronegative than carbon, it's going to have a partial negative charge. And carbon, because it's less electronegative than oxygen, it has a partial positive charge. So how can we indicate bond polarity? How can we show the dipole moment in this bond? You need to draw an arrow pointing towards the more electronegative element. And so whenever you see a dipole moment like this, it tells you that this bond is a polar bond. Now, what about the bond between sodium and chlorine? Would you describe it as ionic, polar covalent, or non-polar covalent? Sodium is a metal. Chlorine is a non-metal. And typically, when you have a metal mixed with a non-metal, for the most part, it's safe to say that it's going to be an ionic bond. Sodium chloride is made up of ions. In this substance, sodium has a positive charge, and chlorine has a negative charge. Positively charged ions are known as cations, and negatively charged ions are known as anions. And so that's why we have an ionic bond. We know that opposite charges attract, and so there is an electrostatic force of attraction that keeps these ions held together, and that makes the ionic bond. So typically, whenever you have a metal mixed with a non-metal, ionic interactions are usually created. Now, it's important to understand the difference between an ionic bond and a covalent bond. In a covalent bond, the electrons are shared. In an ionic bond, the electrons are transferred. So in a polar covalent bond, they're shared unequally, but in a non-polar covalent bond, the electrons are shared equally. Sodium has 11 electrons, but it has 1 valence electron. Chlorine has 7 valence electrons.
Okay.
So when you put together, let me draw this differently, an atom of chlorine and sodium, it's going to give away its 1 valence electron to chlorine. And when it loses that electron, it acquires a positive charge. When chlorine accepts it, it's going to have 8 valence electrons, and so it's going to be negatively charged, since it gained an extra electron. So after this transfer of electrons, there's going to be an electrostatic force of attraction that holds these ions together. And so that makes up the ionic bond. Now let's talk about the hydrogen atoms that make up the H2 bond. Let's say if we have 2 individual atomic hydrogen particles, both of which contain 1 valence electron. When these 2 get together, they will each give up their valence electron to form a covalent bond. And so the 2 electrons represented by that bond are shared equally among those hydrogen atoms, and that's why it's a non-polar covalent bond. The electrons are shared. In an ionic bond, you had a transfer of electrons. Sodium gave up an electron, chlorine accepted it. But here, both hydrogen atoms contributed an electron to give up polar covalent bond. The electrons are shared. In an ionic bond, you had a transfer of electrons. Sodium gave up an electron, chlorine accepted it. But here, both hydrogen atoms contributed an electron to create this covalent bond. And so that's why it's not ionic, but it's covalent. You have a sharing of electrons as opposed to a transfer of electrons. Now let's go through some more examples. So what about the carbon-hydrogen bond? Would you describe it as ionic, polar covalent, or non-polar covalent?
Non-polar.
Now carbon
Polar
has an
covalent.
electronegativity value of 2.5, and for hydrogen it's 2.1. So the electronegativity difference is 0.4, which means that this bond is nonpolar.
Oh,
Whenever you see a molecule that contains only carbon and hydrogen bonds, it's a nonpolar molecule. For example, methane is nonpolar, it doesn't mix with water, or hexane, C6H12, that's a nonpolar molecule.
I see.
They don't dissolve in polar substances like water or like alcohol. Now, what about the carbon-carbon bond? Is it ionic or is it covalent? Now, both substances have the same electronegativity value, so the En difference is 0, which means that it's nonpolar. So anytime you have 2 of the same type of atoms that make up a bond, it's always going to be a nonpolar bond. The electrons will be shared equally. Now, what about the OH bond? What can we say about it? Is it an ionic bond, a polar covalent bond, or a non-polar covalent bond? Well, let's start with the electronegativity values. Oxygen has an electronegativity of 3.5, and for hydrogen it's 2.1. So the electronegativity difference is 1.4. So this bond is highly polar. Now, it's a special type of polar bond. Anytime you see hydrogen directly attached with nitrogen, oxygen, or fluorine, it's a special type of bond. Do you remember what it is? It's known as hydrogen bonding. These are very powerful intermolecular forces. Because of hydrogen bonding, water has a very high boiling point for being a molecule. Most molecules have low boiling points, but those with hydrogen bonds, they have relatively high boiling points. So we have a polar covalent bond with a special case of hydrogen bonding. Now let's indicate the bond polarity. Because oxygen is more electronegative, it's going to have the partial negative charge, and hydrogen is going to have the partial positive charge. So to indicate the dipole moment, we're going to draw the arrow towards the more electronegative element. Now let's consider one more example. What about the bond between lithium and fluorine? Would you say it's an ionic bond, a covalent bond, and if it's covalent, and fluorine? Would you say it's an ionic bond, a covalent bond, and if it's covalent, is it polar covalent or non-polar covalent? Lithium is a metal, fluorine is a non-metal. So automatically, just by identifying the type of element that we're dealing with, we know it's going to be an ionic bond. The electronegativity difference between lithium and fluorine is huge. But for the most part, if you have a metal and a non-metal, it's safe to say that you have an ionic interaction. Lithium is a positively charged cation, and fluoride is a negatively charged anion.
How many stars would a hotel get if every room had a view?
Excuse me.
Great Northern Brewing Co. The beer for up here.
If you do absolutely nothing, AI might take your job.
This class isn't about writing prompts.
You know your job better than anyone.
Consider the bonds between carbon and hydrogen, and also between carbon and oxygen. Which bond is more polar, the carbon-hydrogen bond or the carbon-oxygen bond? In order to determine which one is more polar, we need to look at the electronegativity values of these elements.
I think I can skip this
Carbon
one.
has an electronegativity value of 2.5. And you can look this up in your textbook. Some of the values might be slightly different, but because 1.0 is higher and polar, so it is more polar. As indicate which one is more polar and also indicate the direction of polarity. I'm going to write this as OH instead of HO. So which one is more polar? Now we said that hydrogen has an electronegativity value of 2.1. Oxygen is 3.5, and fluorine is 4.0. Fluorine is the most electronegative element that we know on the periodic table. Now the EN difference for the OH bond is 1.4, and the EN difference for the HF bond, that's 4 minus 2.1, so that's 1.9. So because this has a higher electronegativity difference, we can say that the HF bond is more polar. Now both of these types of bonds, they represent a special class of bonding, particularly hydrogen bonds. Whenever you see hydrogen attached to nitrogen, oxygen, or fluorine, you have a special case of hydrogen bonding. But this is going to be the most polar covalent bond that you have here. Now we need to indicate the direction of polarity. So oxygen is more electronegative than hydrogen, so it's going to have the partial negative charge. Hydrogen is going to bear the partial positive charge. And fluorine is more electronegative than hydrogen. To draw the dipole moment, you need to point the arrow towards the more electronegative element, so you can do it like that. Now, what if you don't know the electronegativity values? Let's say you're taking a test and you just don't remember what the numbers are. What can you do in a situation like that? So here's an example that will illustrate what you can do in such a scenario. So let's consider the carbon-nitrogen bond and the carbon-oxygen bond. So which one would you say is more polar? What you need to do is locate the periodic table. On the periodic table, you'll have hydrogen, boron, carbon, nitrogen, oxygen, fluorine, laid out like that. So notice that we have the same element, carbon. So that's our reference element. So we're comparing carbon and nitrogen to carbon and oxygen. So notice that carbon and oxygen are further apart than carbon and nitrogen, provided that they're in the same row. And so whenever you have two elements that are further away from each other in the same row, they're going to have a greater difference in electronegativity because electronegativity increases towards fluorine. It increases as you go to the right and as you go up across the periodic table. And so the electronegativity difference between carbon and oxygen is going to be greater than carbon and nitrogen. Here are the numbers. Hydrogen is 2.1, boron is 2.0, carbon is 2.5, N is 3.0, O is 3.5, F is 4.0. And so the difference between these two numbers is only 0.5. But the difference between these two numbers is 1.0. So whenever you have two elements that are far apart from each other, typically they will represent a more polar bond than two elements that are closer to each other in the periodic table. So CO is the most polar out of the two that are listed here. Here's another problem for you. List the bonds in order from least polar to most polar. And so let's say we have the carbon-bromine bond, the carbon-iodine bond, the carbon-chlorine bond, and the carbon-fluorine bond. So go ahead and try this. Now we know the electronegativity of carbon is 2.5. But what about the halogens? So let's see if we can do this without using the numbers, but then we'll confirm it with the numbers. On the periodic table, the halogens are listed in this order. Now you need to keep in mind that electronegativity increases as you go up. And so fluorine is the most electronegative halogen in this group. Now given that carbon has the same electronegativity value, we could say that CF is going to be the most polar since it has the most electronegative element in it. And then it's going to go in order. So we want to rank it from least polar to most polar. So iodine has the lowest electronegativity value out of the 4 halogens. So we could say that it's going to be the least polar. So it's going to be Ci, and then that's less polar than CBr, which is less polar than CCl, and that's less polar than CF. So once you identify the most polar group, it's easy to rank everything else based on the way it's laid out on the periodic table. Now let's look at the numbers. So keep in mind, carbon is 2.5. Iodine has an electronegativity value of 2.5. Bromine is 2.8. Chlorine is 3.0. And for fluorine, it's 4.0. So the EN difference, I'm just going to write the number in green. The EN difference between carbon and iodine is 0. The electronegativity difference between these two elements, that's 2.8 minus 2.5, so that's 0.3. And 3 minus 2.5, that's 0.5. And 4 minus 2.5 is 1.5. Now keep in mind, in order to have a polar covalent bond, the electronegativity difference has to be 0.4 or less. So therefore, these two bonds is relatively nonpolar when you just analyze the electronegativity difference alone. The carbon-chlorine bond is considered to be a polar covalent bond, and the carbon-fluorine bond, it's highly polar. So it's the most polar bond in this group, based on the EN difference. Now let's work on one more problem. Consider the bonds carbon and nitrogen, carbon and hydrogen, and then carbon and carbon. So in this example, I'm going to rank it from most polar to least polar, as opposed to the last example, which was least polar to most polar. So go ahead and try it. Feel free to pause the video and give this problem a shot. So what I'm going to do is use the electronegativity values in this case. So by this time, we know what the EN value for carbon is. It's 2.5. And for hydrogen, it's 2.1, and it's 3.0 for nitrogen. Therefore, the electronegativity difference for the CN bond, it's going to be 0.5. For the carbon-hydrogen bond, it's going to be 0.4. And for the carbon-carbon bond, it's 0. Whenever you see a bond that consists of the same type of atom, like in that example, carbon and carbon, you know that it's going to be a nonpolar bond. The electronegativity difference will be 0. So this automatically is the least polar. So the most polar is going to be the carbon-nitrogen bond, and then that's more polar than the carbon-hydrogen bond, which is more polar than the carbon-carbon bond. And so this is the way that we could rank it. The carbon-nitrogen bond is polar because it has an EN difference of 0.5. The carbon-hydrogen bond is considered to be nonpolar, and the carbon-carbon bond is completely nonpolar. In this lesson, we're going to talk about electrostatic potential maps. Now, you're most likely to encounter this topic either in your first or second chapter of organic chemistry. And you might be wondering, what is an electrostatic potential map? Well, let's think about the words electrostatic. I think of static electricity. Static means stationary. In this case, the electrons, they're stuck on the atoms being examined. You also have dynamic electricity. Think of electricity flowing through a wire. Now, what about potential? Think of the word electric potential. Perhaps you're familiar with the word voltage. Think of a 1.5 volt battery. Voltage is basically the difference of two potentials. So let's say at point A, the electric potential is 300, and at point B is 500. Voltage is the potential difference between those 2 points, which will be 200. The electric potential at A is 300 volts. The electric potential at B is 500 volts. So B has a higher electric potential than A. So when you think of the word electrostatic potential, think of electric potential in the sense of voltage, but also charge as well. In physics, the electric potential of a charge is dependent on the electric charge. So let's say if you have a positive charge with a Q value of 100 microcoulombs, at a distance of 1 meter away from that charge, it's going to create an electric potential, and we can plug it in this formula. K is 9 times 10 to the 9, Q is 100 times 10 to the minus 6, and at a distance of 1 meter, this charge will create an electric potential of 900 volts. Now, let's say if we double the charge. Instead of Q, let's say it's 2 times the value of Q, or 200. So if we double this number, at the same distance of 1 meter, the electric potential will double to 1800 volts. So as the electric charge increases, the electric potential increases. Now you might be wondering, why am I talking about physics when this topic is for organic chemistry students? Now the reason I mention this is to help you see that there's a direct relationship between electric charge and electric potential. They're directly related. The electrostatic potential map, it tells us how electric charge is distributed among a molecule. But this map doesn't have the word charge in it. It has the word potential. So the question is, why is that? Now, this map is neatly color-coded in line with the visible spectrum. Think of RGB, red, orange, yellow, green, blue, violet. Now, the orange-red areas, that's where you have a region of negative charge. So if you see a molecule that has a red-orange color to it, that's the negatively charged part of the molecule. The blue area represents the positively charged region. So in this way, the electrostatic potential map, it helps you to see how charge is distributed in the molecule. Now remember, charge is related to potential. As the charge increases, the electric potential increases as well. So as you move to the right, the charge density increases. In this case, we could say the electron density because electrons carry negative charge. So the electron density increases as you move to the right. The more electrons that you have in an area, the greater the charge. Keep in mind, each electron has a charge of negative 1.602 times 10 to the negative 19 coulombs. So if you have 2 electrons, the charge will be negative 3.2 times 10 to the negative 19 electrons. So the more electrons that you have in a region, the greater the charge. And then as the charge increases, the electric potential increases. So the color red has a more negative electric potential than the color orange. You have more electrons.
This game, you're not ready for it.
You're in the middle of this beautiful sci-fi environment. And you're seeing intrigue, the espionage, the alliances form, the power that shifts around. And it's amazing to watch.
Simple actions can have massive effects.
You can cooperate with people, compete with them, make friendships, deceive them, betray them.
In the red region, you have more negative.
My bad, I was hungry.
I'm just going to put a number here. It might be negative 100 microcoulombs. Consider the bonds between carbon and hydrogen as the least polar. So the most polar is going to be the carbon-nitrogen bond, and then that's more polar than the carbon-hydrogen bond, which is more polar than the carbon-carbon bond. And so this is the way that we can rank it. The carbon-nitrogen bond is polar because it has an EN difference of 0.5. The carbon-hydrogen bond is considered to be nonpolar, and the carbon-carbon bond is completely nonpolar. In this lesson, we're going to talk about electrostatic potential maps. Now, you're most likely to encounter this topic either in your first or second chapter of organic chemistry. And you might be wondering, what is an electrostatic potential map? Well, let's think about the words electrostatic. I think of static electricity. Static means stationary. In this case, the electrons, they're stuck on the atoms being examined. You also have dynamic electricity. Think of electricity flowing through a wire. Now, what about potential? Think of the word electric potential. Perhaps you're familiar with the word voltage. Think of a 1.5 volt battery. The voltage is basically the difference of two potentials. So let's say at point A, the electric potential is 300, and then at point B is 500. Voltage is the potential difference between those 2 points, which will be 200. The electric potential at A is 300 volts. The electric potential at B is 500 volts. So B has a higher electric potential than A. So when you think of the word electrostatic potential, and A is the potential difference between those 2 points, which will be 200. The electric potential at A is 300 volts. The electric potential at B is 500 volts. So B has a higher electric potential than A. So when you think of the word electrostatic potential, think of electric potential in the sense of voltage, but also charge as well. In physics, the electric potential of a charge is dependent on the electric charge. So let's say if you have a positive charge with a Q value of 100 microcoulombs, at a distance of 1 meter away from that charge, it's going to create an electric potential, and we can plug it in this formula. K is 9 times 10 to the 9. Q is 100 times 10 to the minus 6. And at a distance of 1 meter, this charge will create an electric potential of 900 volts. Now, let's say if we double the charge. Instead of Q, let's say it's 2 times the value of Q, or 200. So if we double this number, at the same distance of 1 meter,
10 to the 2.
the electric potential will double to 1800 volts.
What?
So as the electric charge increases, the electric potential increases. Now you might be wondering, why am I talking about physics when this topic is for organic chemistry students? Now the reason I mention this is to help you to see that there's a direct relationship between electric charge and electric potential. They're directly related. The electrostatic potential map, it tells us how electric charge is distributed among a molecule. But this map doesn't have the word charge in it. It has the word potential. So the question is, why is that? Now, this map is neatly color-coded.
My bad, I wasn't listening.
The electrostatic potential map, it tells us how electric charge is distributed among a molecule. But this map doesn't have the word charge in it. It has the word potential. So the question is, why is that? Now, this map is neatly color-coded in line with the visible spectrum. Think of Boiii, red, orange, yellow, green, blue, violet. Now, the orange-red areas, that's where you have a region of negative charge. So if you see a molecule that has a red-orange color to it, that's the negatively charged part of the molecule. That is when the electric potential will double to 1800 volts. So as the electric charge increases, the electric potential increases. Now you might be wondering, why am I talking about physics when this topic is for organic chemistry students? Now the reason I mention this is to help you to see that there's a direct relationship between electric charge and electric potential. They're directly related. The electrostatic potential map, it tells us how electric charge is distributed among a molecule. But this map doesn't have the word charge in it. It has the word potential. So the question is, why is that? Now, this map is neatly color-coded in line with the visible spectrum. Think of Boiii, red, orange, yellow, green, blue, violet. Now, the orange-red areas, that's where you have a region of negative charge. So if you see a molecule that has a red-orange color to it, that's the negatively charged part of the molecule. The blue area represents the positively charged region. So in this way, the electrostatic potential map, it helps you to see how charge is distributed in the molecule. But now remember, charge is related to potential. As the charge increases, the electric potential increases as well. So as you move to the right, the charge density increases. In this case, we could say the electron density because electrons carry negative charge. So the have a region of negative charge. So if you see a molecule that has a red-orange color to it, that's the negatively charged part of the molecule. The blue area represents the positively charged region. So in this way, the electrostatic potential map, it helps you to see how charge is distributed in the molecule. But now remember, charge is related to potential. As the charge increases, the electric potential increases as well. So as you move to the right, the charge density increases. In this case, we could say the electron density because electrons carry negative charge. So the electron density increases as you move to the right. The more electrons that you have in an area, the greater the charge. Keep in mind, each electron has a charge of negative 1.602 times 10 to the negative 19 coulombs. So if you have 2 electrons, the charge will be negative 3.2 times 10 to the negative 19 electrons. So the more electrons that you have in a region, the greater the charge. And as the charge increases, the electric potential increases. So the color red has a more negative electric potential than the color orange. You have more electrons.
Do you know what this is? This is a miracle. This is magic. This
have more negative charge, and you have a higher negative electric potential.
Yes, sir.
Now going in the other direction, we're going towards the positive charge. So, by the way, this V is a negative value. When I mean that it's going up, I mean that it's becoming more negative. I'm going to put some numbers to it soon. So going to the left, the charge increases, but in a more positive way. The electric potential increases. Now, because we're dealing with positive charge, this can mean 2 things. It can mean that we have more protons, because protons carry a positive charge, or it can mean that we have the absence of electrons. Now, in the majority of cases, protons, they're basically fixed in the atom. The protons, which are found in the nucleus, they don't really move. So when dealing with chemical reactions, it's the electrons that typically move. So in the context of organic chemistry, we could say that the red areas are electron rich. The blue areas are electron poor. We have a deficiency of electrons in the blue areas, given that the protons are basically stationary in the nucleus of an atom. So the areas where it's electron rich, that's the nucleophilic region of the molecule. Nucleophiles are nucleus 11. They are electron-rich molecules. They tend to have a lot of lone pairs or negative charge. The electron-poor areas, those are the ones with a positive charge or an empty p orbital. Those are the ones that are deficient of electrons, so they're electrophilic. The word phile means loving. So an electrophile, it loves electrons. It wants electrons. It's electron poor, so it really wants it. This video is for those of you who are thinking about joining my Patreon membership program. You can access it at patreon.com/mathsciencetutor. Now we're going to focus on the organic chemistry. Now let's put some numbers to this graph, just to really help you to see the value of this tool. So the middle area, that is the green-yellow area, this area is neutral. So think of it as 0 on a number line. It has a charge value of 0, meaning you have an equal number of protons and electrons, so it's electrically neutral. And if there's no charge, there's no potential. The electric potential is 0. V is equal to K Q over R. So if Q is 0, V is 0. Now, as we get closer and closer to the red side, to this graph, just to really help you to see the value of this tool. So the middle area, that is the green yellow area, this area is neutral. So think of it as 0 on a number line. It has a charge value of 0, meaning you have an equal number of protons and electrons, so it's electrically neutral. And if there's no charge, there's no potential. The electric potential is 0. V is equal to K Q over R. So if Q is 0, V is 0. Now, as we get closer and closer to the red side, it becomes more negative. So Q might be, I'm just going to put a number here, it might be negative 100 microcoulombs. Over here, Q might be negative 500 microcoulombs. So at this point, the potential might be negative 200 volts. Well, let's just say negative 100 volts, just to keep things simple. And over here, it might be negative 500 volts. So as you move towards the right, the electric potential is becoming more negative. So you could say the absolute value of V is increasing, but V is really decreasing if you look at negative values as being lower than positive values. But the absolute value of Q is increasing, but the real value of Q is becoming more negative. So I just want to clarify that point. So the arrow that's going down, it just means that they're becoming more negative. Now on the other side, let's say this light blue region, Q is going to be positive. So it might be positive 100 microcoulombs. And the electric potential is going to be positive 100 volts.
I will master organic chemistry.
As we get to the more darker blue areas, it's going to be even more positive. So this might be positive 500 microcoulombs with an electric potential of positive 500 volts. So I want to help you to see the numbers here. So just to recap, as you move to the right towards the red area,
I will master organic
it becomes
chemistry.
more negatively
I will
charged,
master organic chemistry.
and the electric potential is decreasing, it's becoming more negative. As you move towards the left, towards the blue areas, the charge is increasing in a more positive way, and the electric potential is also positive. So the potentials are high at either side, but in the middle it's 0. On the right side it's negative, on the left side it's positive. Now let's work on a practice problem. So here we have electrostatic potential maps of different molecules and ions on the right side, and we want to match it to the appropriate substance.
Okay, 4C.
So how can we do this?
4C.
Remember,
B
red
is
represents
B.
negative, blue is positive, green is neutral.
H3O is
So looking at the molecules that we have, we know that HF and
H2O
water
is
are
3.
polar. When you're dealing with polar
H2O is
molecules,
3.
you have one side is positive, one side is negative. So that means you're going to have blue and red there. Hydrogen is nonpolar, which means it's neutral. So we should expect hydrogen to have the green color. Therefore, this should be H2. We don't see two different colors. So because we see one color, it's nonpolar and it's neutral. There's no separation of charge. So number 2 is B. Now let's focus on the last two, H2O plus and hydroxide. We know that positive charges correlate to a blue color, negative charges correlate to a red color. Now we're dealing with ions, particles with a net charge. So because H2O plus has an overall net positive charge, we should expect that the entire particle, for the most part, should be predominantly blue. Hydroxide has an overall negative charge, so we should expect that the entire particle will be mostly red. So looking at all our options, D is mostly red, that's going to be hydroxide. E is, for the most part, blue, and that's going to be H2O plus. And of course, we can see that there's 4 atoms here, so that's going to indicate that it's H2O plus. It's the only option with 4 atoms. So number 5 is D, and number 4 is E. Now, what about number 1 and number 3? HF and H2O, they're polar molecules. Polar molecules, you're going to have 2 colors, or at least 2 predominant colors, red and blue. So looking at HF, fluorine is partially negative. So this is going to be the red side. And hydrogen is partially positive. That's going to be the blue side. Now if we focus on water, I'm going to draw it out. That's water. Oxygen is electronegative, so it's going to carry the partial negative charge. It's going to be red. And hydrogen is going to be partially positive, blue. And looking at the shape of this molecule, we can see 2 blue regions. That's the 2 hydrogen atoms. And we can see the red region, which is the oxygen. So C has to be water. For A, this has to be HF. So the red region represents fluorine. The blue region, notice that it's smaller here, that's hydrogen.
From idea to submission, empower students to do their best work with Grammarly's comprehensive AI writing assistance.
This is what we've learned as it relates to polarity. Nonpolar molecules, they tend to have basically one color, like a greenish yellow color. As we saw in the case of hydrogen, we didn't see 2 distinct colors, basically one color. And around the yellow-green area, we know that the potential is 0. That's the region where it's electrically neutral. So you don't really have separation of charge, as in the case of a polar molecule. So when dealing with polar molecules, like HF, we saw 2 major colors, a red area and a blue area. The blue area was for hydrogen, and the red area was mostly for fluorine. Now, of course, there was some yellow and green in between. But for the most part, if you see one side red and the other side blue, that's an indication that you're dealing with a polar molecule. One side is partially positive. In this case, that's the hydrogen side. And then the other side is partially negative. Now, the other part has to do with ions. So if you see an overall blue color, that means you're dealing with a positively charged ion. If you see an overall red color, or orange-red, the more red it is, the more negative it is. You're dealing with a negatively charged ion. So hopefully, this will help you to distinguish a polar molecule from a nonpolar molecule from an ion using electrostatic potential maps. Now let's consider the electrostatic potential maps of hydrogen, methane, and ammonia. Now when you see green or yellow-green, for the most part you're dealing with nonpolar molecules. When you see clear, distinct colors of red and blue, you're dealing with polar molecules. The red area has a very high negative electric potential. The blue area has a very high positive electric potential. When you see green and yellow, the electric potential is more closer to zero, rather than being far apart, either in the positive side or in the negative side. Now, when we look at hydrogen, hydrogen has an electronegativity value of 2.1. So the electronegativity difference in this bond is 0. Now, when we focus on methane, particularly the carbon-hydrogen bond, the EN difference is not 0. Carbon has an electronegativity value of 2.5, and for hydrogen it's 2.1. So we have an EN difference of 0.4. In order to have a polar bond, the electronegativity difference is defined to be 0.5 or higher. So the CH bond is just below that threshold. Now for a polar molecule, like ammonia, there is a significant difference. Nitrogen has an electronegativity value of 3.0. So we have an EN difference of 0.9. So we can see why ammonia is polar. So looking at hydrogen, we can see why, for the most part, it's virtually a solid green color. We don't see separation of colors here. We basically see, for the most part, one distinct color. And the reason being is there's not much electronegativity difference between the two hydrogen atoms. For methane, there is a small difference, and we could see some color variation. We can see the hydrogen is more on the green side, whereas the carbon, it's a little more electronegative. We can see it's a different color. It's more on the yellow side. Now, going back to our electrostatic potential spectrum, we had red, orange, yellow, green, and blue. Now remember, blue is positive and red is negative. So when you're dealing with red and blue, you're dealing with a polar molecule. You're dealing with a more polar molecule, so to speak. When you're dealing with yellow and green, that's closest to the middle, you're dealing with a less polar molecule, or even a non-polar molecule. So hydrogen is green, and the carbon is more on the yellow-orange side. Let's put yellow for carbon. So green is more positive, and yellow is more negative. As we can see, green is more on the positive side, yellow is closer to the negative side. And that's what we see here. So just to recap, if you see a molecule with one side red, one side blue, you're dealing with a highly polar molecule. If you see just one uniform color, either yellow or green, you're dealing with a non-polar molecule. If you see like one region green, one region yellow, either it could be a non-polar molecule, like a CH bond, or it could be a slightly polar molecule. So hopefully that helps you to see how you can use electrostatic potential maps to not only identify molecules, but to determine if you're dealing with a polar molecule, a non-polar molecule, or even an ion.
I tried everything: coffee, Pomodoro, and binaural beats, but nothing stuck until I tried this. Brain FM is neuroscience-backed music designed to help people who struggle with focus. Instead of fighting distractions, your brain just enters flow. Try it for free and slip into effortless focus.
What if you could taste the movies?
We turned that idea into an $11.3 million business with Wix. One movie night, we were craving this chocolate cake that we...
In this video, we're going to talk about how to draw some basic glue structures within the realm of organic chemistry.
I'm not gonna lie, I might have to end stream.
So let's go over some basic things you need to know. Hydrogen
I'm looking tired as well. W stream or what? Alright, peace out, guys. Go. Actually, we go to the 1 hour mark.
Can only form one bond. Elements like boron, carbon, nitrogen, oxygen, fluorine, they can form multiple bonds. Boron likes to form 3 bonds when it's in its neutral state. Now, when it has a charge, it can deviate from this number. Carbon, in its neutral state, likes to form 4 bonds. Nitrogen likes to form 3, oxygen likes to form 2, and halogens like to form 1. So like fluorine, chlorine, bromine, iodine, those elements, they like to form 1 bond. They have 7 valence electrons, and they only need 1 more to get to 8. Sulfur likes to form 2 bonds, but sometimes it can form 6. It has 6 valence electrons. It can either try to acquire 2 to get to 8, so in that case it's going to form 2 bonds, or it can give away 6 valence electrons and form 6 bonds in the case of sulfate. Phosphorus, like nitrogen, likes to form 3 bonds. Silicon, like carbon, likes to form 4 bonds. But these are the most common elements that you're going to be dealing with in organic chemistry. So let's say if we want to draw a Lewis structure for methane, you know that carbon likes to form 4 bonds, and hydrogen can only form 1 bond. So the only way to put this together is to do it like this. And so that is the Lewis structure of methane. What about this example? Methanol, CH3OH, a type of alcohol. So you have only 1 bond, carbonless here, Lewis with 3 hydrogen atoms. And then we have CH2. Now nitrogen likes 1 over here. Alright, let's draw the Lewis structure for that. Now let's work on another example. Dimethyl ether. Go ahead and draw the Lewis structure for that. So I'm going to start with oxygen in the middle. Oxygen likes to form 2 bonds, and on each side you have a methyl group, or CH3 group. And we know each of those carbons contain 3 hydrogens. And an oxygen, when it has 2 bonds, it's going to have 2 lone pairs. And so that's the Lewis structure for dimethyl ether. Now what about this one, CH3CHO? How can we draw the Lewis structure for this molecule? So the left side, CH3, at this point we're pretty familiar with it. It's just a carbon with 3 hydrogens. Now this carbon needs 4 bonds, so we're going to draw another bond. And the next thing that it's attached to is carbon atom. Now how can we draw CHO? Well, we can't draw it like this because hydrogen will have 2 bonds and that's not going to work. And we can't draw it this way because carbon will have 4 bonds. The only way in which we can make carbon to have 4 bonds and hydrogen to have 1 and oxygen to have 2 is to put a double bond between carbon and oxygen and connect carbon directly to hydrogen. As you can see, every element has their desired number of bonds. And so this is the Lewis structure, CH3CHO. This is a type of aldehyde, specifically acetaldehyde. This is how you spell the name. Aldehydes typically have this functional group that you see here. Next up is C2H4. Go ahead and try that. Draw the Lewis structure of that molecule. So how should we begin? Are the 2 carbons connected to each other, or how do you even draw this thing? When you see something like this, draw the carbon atoms first. Now there's 4 hydrogens. The best thing to do is to split the number of hydrogens equally among the 2 carbons. You don't want to put 3 hydrogens on 1 carbon and then 1 hydrogen on the other, because the carbons are the same, so they're going to have the same attraction to those hydrogen atoms. The best thing to do is to draw the molecule with symmetry. So begin by putting 2 hydrogen atoms on each carbon. Now you know that carbon wants to have 4 bonds, and right now each carbon atom has 2. So the only way to make each carbon atom have 4 bonds is to put a double bond in the middle. And so that is the structure of C2H4, also known as ethene. It's a type of alkene. So anytime you see a double bond between 2 carbon atoms, the functional group is an alkene. Now let's move on to our next example, and that is C2H2. Go ahead and try that one. So let's start with 2 carbon atoms, and we're going to put a hydrogen on each one. Now the only way for each carbon atom to have 4 bonds is to put a triple bond in the middle. And so this molecule is known as acetylene. And the functional group is an alkyne, which corresponds to a triple bond between 2 carbon atoms. Now what about this molecule, hydrazine? How can we draw the Lewis structure for it? Now this is going to be very similar to C2H4. So we're going to put the 2 nitrogen atoms in the middle, and we're going to start by placing 2 hydrogen atoms on each nitrogen atom. Now we know that nitrogen likes to form 3 bonds, so right now each of them have 2, which means that we need a single bond between the 2 nitrogen atoms. Now nitrogen likes to have 1 lone pair, so we can draw that way. So that's the structure of hydrazine. Now let's talk about what to do when you have charges. So I want you to draw these 3 molecules, CH3O-, CH3OH, and CH3OH2+. So let's start with a familiar example, one that we covered already, methanol. You know what, I'm not going to draw the CH3 part. I'm just going to leave it like this, CH3. Now the OH part is what I'm going to focus on. So we know that oxygen likes to form two bonds, and so it's going to have two lone pairs. But what's going to happen if we take off the hydrogen on the oxygen? The two electrons in this bond, they're going to be pulled back to the oxygen. Oxygen is more electronegative than hydrogen is, so it has a partial negative charge. And so when this bond breaks, those electrons will be returned to the more electronegative elements and be pulled by it. And so this oxygen is going to have 3 lone pairs as opposed to 2, and now it has a negative charge. Now what about if the oxygen gains hydrogen? What's going to happen? What we're going to do is react methanol with a hydrogen ion. Now we said that oxygen has a partial negative charge, and so it's attracted to the positively charged hydrogen ion. And so it's going to use a lone pair to form a bond between the oxygen and the incoming hydrogen. And so we're going to get a structure that looks like this. I'm running out of space here. So this lone pair is gone, and those electrons are now in this bond. And so this oxygen has 1 lone pair left, but now it bears positive charge. And so whenever you have an oxygen with positive charge, note that it loses a lone pair to form a new bond. And when it has negative charge, it gains a lone pair to break a bond. So as you can see, whenever you have charges, oxygen won't have 2 bonds. When it has a negative charge, it typically has 1 bond. When it has a positive charge, it typically has 3 bonds. When it's neutral, it has its standard number of 2 bonds. So those are some things you want to keep in mind. But that's it for this video. That's all I got. Thanks for watching.
Bulk Nutrients Protein Water combines collagen, whey protein,
Go ahead and consider the structure CH3, CH2, CH2 times 3, CH2OH. Go ahead and draw the calculate structure of this particular condensed structure. Now, a calculate structure is like a Lewis structure, with the exception that the lone pairs are usually omitted. So we're not going to worry about drawing the lone pairs on oxygen. So go ahead and draw the calculate structure for this molecule. So let's start with the carbon on the left. So that carbon has 3 hydrogens attached to it. Next, it's attached to a CH2 group. So we have a carbon with 2 hydrogens, and then we have 3 CH2 groups. So that's going to be 3 carbons, all connected to each other, each with 2 hydrogen atoms. And then we have another CH2 group with an OH at the end. And so this is the calculated structure of this particular condensed structure. Here's another example you can work on. Draw the calculated structure of CH3, CH, Br, CH2, C, CH3 times 3. Take a minute and work on that example. So starting with the carbon on the left and working our way towards the right, that carbon has 3 hydrogen atoms attached to it. And then it's attached to a carbon atom, which has a hydrogen, and it has a bromine atom attached to it as well. And then after that, we have a CH2. So that's a carbon with 2 hydrogens, and that's attached to another carbon, and that carbon has 3 methyl groups. Now, whenever you see a CH3 group, it's always at the end. It can never be in the middle. And this is a CH3 group as well. CH and CH2 groups, you can have that in the middle of the chain. But CH3 groups, they always tend to stick outside of the chain. They can't be in the middle. Now, here's another example. CH3, CH, CH3, CH2, CH, OH times 2. What about that example? It looks like we have a CH3 in the middle. So what should we do if we see that? So let's start with the CH3 on the left. So we have a carbon with 3 hydrogen atoms, and then we have a CH group. Oops, that's a carbon.
Let me try this real quick. CH. That. And then like this. And then C. Wait. Oh, wait, hold on now. H. No. Bang.
Carbon with a hydrogen. Now, this particular CH3 group, we cannot write it like this, and then attach a CH2 next to it, because carbon can't have 5 bonds. If you were to expand it and write it as CH3 and then CH2, it wouldn't make sense. You can't have a carbon with 5 bonds. So that's why you can't put a CH3 group in the middle. So in this case, we need to put the CH3 group outside of the chain. So I'm going to highlight that in red. And then after that, we can place the CH2 group in the middle of the chain. And then we have a CH, so that's a carbon with one hydrogen atom, and that carbon is attached to two other OH groups, which I'm going to highlight in red. And so that's the calculated structure for this particular condensed structure. Now let's consider one more example. CH3, CH2, C, CH3 times 2, and then CH2, CH, Cl, CH2, CF3. Go ahead and work on that example. So let's start with the carbon on the left. We have 3 hydrogens attached to it. And then we have a CH2, so a carbon with 2 hydrogens. And then we have another carbon with 2 methyl groups. So I'm going to highlight that in blue. And then there's a CH2 group, a carbon with 2 hydrogens. And then we have CHCl. So we have carbon with a hydrogen and with a chlorine atom, which I'll highlight in green. And then it's a CH2, and then CF3. So the last carbon has 3 fluorine atoms. And so that's it. That's how you can write the calculated structure or the expanded Lewis structure for this particular molecule.
W stream.